Let's use the Riemann sum to compute an area. What we want to do is compute the area bounded by the following curves. That is f equal x squared minus 2x plus 2, y equals 0, x equals 0, and x equals 1. Of course, this is the x-axis and this is the y-axis. Now, what I've done here, just to show you a little bit more about this quadratic function, is I've completed the square, and it's always positive. But the idea is that this easily gives us a vertex of 1, 1. And now when we sketch in the quadratic function and the other lines, we see that this red shaded area is what we're interested in computing. Now, what we want to do is partition the interval from 0 to 1. Of course, it will have length 1. But now the actual evaluation point will be much simpler. We can just use right endpoints and let c sub I be I divided by n. Again, very simple. So c sub I minus 1 will just be I minus 1 over n. And then when we take the difference between these two, the I sub n's absorb and we're just left with 1 over n. That's what we call a regular partition, because the length of the I subinterval is the same for every subinterval, and that makes the computation easier. Now, in this particular case, the area will now be the limit of the Riemann sum. So we evaluate f at the c sub I, and we multiply by the length of the ith subinterval. So here we go to the red box. So we have I over n squared minus 2 times I over n plus 2. And then, of course, we have a regular partition. So the length of the I subinterval is just 1 over n. Now remember, these are just sums with index variable I, so the n's don't have any impact there. So what we can do when we square the n, we can just pull it out. Here, this n we can also factor. And then, of course, there's not much here to worry about. And of course, I factored the -2 here just to make the computation easier. So now we have our famous sum formulas. What's nice about pre-calculus is that we learn these formulas so we don't have to start from scratch when we get to calculus. So when we sum the first n squares, we use the formula n times n plus 1 times 2n plus 1 divided by 6. And of course, when we sum the first n counting numbers, we use n times n plus 1 divided by 2. And then, of course, here, and then need a plus here, when we add 1 to itself n times, we just get n, so we get 2n for that particular sum. Now, the way I've set this up, I want to keep it simple for you. The evaluation of these limits is very simple if you keep everything factored. Now what we can do is move in the n, so we have 3 copies of n to spread across these 3 factors, n over n, n plus 1 over n, 2n plus 1 over n. To multiply all this out would be a complete waste of time. And now here, we do the same thing. The 2's absorb. We move in the n to join that n, so we have n over n here, and n plus 1 over n. And then, of course, the n and the 1 over n here absorb and just leave us with a 2. Now it's very simple to pass to the limit. Of course, here, 1, 1, 2, and a 6. So we get 2 over 6. Here, we just have a 1, 1, so we get 1 with the negative sign. And of course, that's constant, so that's 2. So we just get what? 1 over 3 plus a 1, which is 4/3. So this computation was simpler than the square root because the evaluation point, the c sub i's, was much easier. But what we saw with that particular problem is that this process is actually computing a definite integral. So as we continue and as we have defined the definite integral, we will be very interested in knowing how to compute this. That is, we don't have to do this every time, and we know what that means, but how do we compute it? And we will actually find that out when we study the fundamental theorem of calculus. And we are done.